Last episode gave Kestrel services something they'd never had before: verified identity for every connection, enforced at the mesh layer. So a request from the billing service to the scheduling service could prove it actually was the billing service. That answers one question: who is calling? It says nothing at all about a second question that matters just as much. What is this caller actually allowed to do? Istio's MTLS layer can tell you a request is genuinely from the billing service. It can't tell you whether the billing service should be allowed to read a specific patient's payment history through that particular endpoint at that particular moment. That's a different problem. And after the identity rebuild, Kestrel discovered it had answered that second question in about 6 different ways, none of them consistent with each other. Here's how this happens, and it's worth being specific because it's rarely one bad decision. It's dozens of individually reasonable ones. A microservices estate grows one service at a time, usually built by different teams, often months or years apart. Each team, when it hits the question of who's allowed to do what, solves it the fastest way available, right there in the code they're already writing. One team writes a conditional straight into a request handler. If the user's role field equals admin, allow the write. Another team, needing something slightly more flexible, builds a permissions table in their own services database and checks against it. A third team, working somewhere authorization checks feel like an afterthought, hard codes the logic into a shared piece of middleware that nobody has fully documented and everybody is now afraid to touch. None of these choices is unreasonable in isolation. Each one solves that team's immediate problem on schedule with the tools already in front of them. The failure isn't in any single decision. It's in what accumulates across dozens of those decisions, made independently, with no shared model connecting them. At Kestrel, post-rebuild, this is exactly what happened. The billing service checked permissions with a role string compared directly in application code. The scheduling service checked against a table of user-to-resource mappings it maintained itself. A newer reporting service, built by a team that had read about attribute-based access control, checked a combination of user attributes and resource tags, using logic that existed nowhere but that one service's source file. It would be easy to file this under general code hygiene and move on, but the actual damage is architectural, not cosmetic. Consider what happens when Kestrel faces a compliance review and someone asks a question that sounds like it should have a simple answer. Who, across the entire estate, can access a given patient's billing records and under what conditions? Answering that, honestly, now requires opening every service's source code, one at a time, and reverse engineering each team's private logic back into plain language, because there is no single place that logic lives, and no shared vocabulary between the 3 versions of it that exist. That's the audit problem. There's a consistency problem sitting right alongside it. The billing service's role check and the scheduling service's permissions table can drift out of sync in ways nobody notices until an incident forces the question. A contractor whose access should have been revoked everywhere might still have it in exactly one service, because revocation only ever touched the 2 systems someone remembered to update. And there's a change problem too. A new compliance requirement, something as ordinary as an added restriction on after-hours access to a certain record type, now has to be implemented 3 separate times, in 3 different languages and data models, by 3 teams who may not even know the other 2 versions exist. Get one of the 3 wrong, and you have a policy that's enforced everywhere, except the one place it quietly isn't. Open Policy Agent, OPA, is a general-purpose policy engine, and it's a real, mature project. It graduated from the Cloud Native Computing Foundation, the same foundation that stewards Kubernetes and Istio, which is a useful signal about how embedded it already is in this part of the ecosystem. The core idea is narrower and more useful than it might sound. Take the authorization decision itself, the is this allowed logic, and pull it completely out of application code into a dedicated engine that any service can query with a structured question and get back a structured answer. That's the whole shift, and it's worth stating plainly because it's easy to overcomplicate. Instead of the billing service containing its own opinion about who can do what, the billing service asks OPA. Instead of the scheduling service maintaining its own permissions table, the scheduling service asks the same OPA the same way. The policy logic itself stops being duplicated, reinvented, and drifting, because it stops living inside any individual service at all. OPA's policies are written in Rego, its purpose-built declarative language, and it's worth understanding the shape of it conceptually, rather than treating it as arbitrary syntax to memorize. A Rego policy isn't a sequence of steps to execute. It's closer to a set of rules describing what must be true for a decision to come out as allow. You feed it structured input, who's asking, what they're asking to do, what resource they're asking about, and the policy evaluates that input against rules that reference both the request itself and reference data the policy has been given, like a list of roles or a table of resource ownership. The output is a decision, typically as simple as allow or deny, though it can return richer structured results when a caller needs more than a yes or no. The reason this matters architecturally is that a Rego policy reads like a specification of intent, not an implementation detail buried inside a request handler. A user may update a billing record if they belong to the billing team and the record isn't already closed, can be written close to that literal sentence. As a rule, version controlled and readable by someone who didn't write the surrounding service at all. That readability is not a minor bonus, it's a big part of what actually fixes the audit problem, because the policy itself becomes the answer to who can access what, rather than something you have to reverse engineer from scattered code. The architectural pattern underneath all of this has a name worth knowing precisely, because it clarifies what OPA is and, just as importantly, what it deliberately isn't. OPA is a policy decision point. A PDP, its only job is to answer the question, is this allowed, given a request and the rules that apply to it. It does not intercept traffic, and it does not enforce anything itself. That enforcement job belongs to something else entirely. The policy enforcement point, the PEP, whatever component actually sits in the path of the request and is capable of blocking it. A PEP might be a sidecar proxy, an API gateway, or application code that calls out before proceeding. This is exactly where last episode connects directly to this one. Istio's sidecar proxy, sitting alongside every service in the mesh, is a PEP. Right now, in Kestrel's Arc3 opener, that sidecar enforces MTLS-based identity and mesh-level allow, deny rules on its own. Istio can also be configured to call out to OPA for the authorization decision itself. The sidecar stays the enforcement point, intercepting the request and capable of blocking it. But the decision of whether to allow it gets delegated to OPA as an external authorizer. The sidecar asks, OPA decides. The sidecar enforces whatever OPA returns. Identity answers who's calling. This layer, PDP and PP together, answers what they're allowed to do, and it means Kestrel doesn't have to choose between the mesh-level enforcement Istio already gives it and a single, consistent authorization model. The two compose. In practice, OPA gets deployed as a sidecar alongside each service, or in some setups as an embedded library the service calls directly. The deployment shape is flexible. and which one a given service uses is mostly an operational choice, not an architectural one. What doesn't change across those choices is the discipline this pattern enables. Policies live in Rego files, in version control, alongside the rest of the code base. They go through the same review process as any other change. They can be unit tested the same way you'd test any function. Given this input, does the policy return allow or deny, and does that match what the policy is actually supposed to guarantee? This is what policy as code means in practice, and it's a genuinely different posture from what Kestrel had before. A permissions table buried in a services database doesn't get code reviewed the way a pull request does. A conditional hard-coded into a request handler doesn't show up in a diff labeled authorization change. It shows up as an unremarkable line in a much larger commit, easy to miss, easy to approve, without anyone clocking what it actually changed. Rego policies, checked in as their own files with their own tests, make an authorization change visible as exactly what it is, to exactly the people who need to review it. It's worth being precise about what's actually being centralized here, because the natural assumption, one OPA service everyone calls over the network, isn't the point, and isn't even how OPA is usually deployed. OPA is designed to run in a distributed way, often as a sidecar next to every service, evaluating locally rather than making every authorization check a network round trip to some central authority. What's centralized isn't the physical process, it's the decision model, the actual rules, written once, in one place, in one language, and distributed out to wherever they need to be evaluated. That distinction is what actually fixes Kestrel's two problems. The audit question, who can access what, everywhere, now has a real answer, because every service's authorization logic is expressed as Rego policy, sitting in one version-controlled repository, readable end-to-end, rather than scattered across 3 code bases in 3 different shapes. The consistency question is fixed the same way. When a new compliance requirement comes in, it's written once, as a policy change, tested once, and every service that queries OPA picks up the same rule the moment it's deployed. Not 3 separate implementations that can silently drift apart. Kestrel's billing, scheduling, and reporting services each still run their own local OPA instance for speed and for resilience against a single point of failure. What they no longer have are 3 private, incompatible opinions about what allowed means. So Kestrel now has verified identity from the mesh and a single consistent authorization model answering what that identity is allowed to do. There's still a gap between those 2 things and full containment, and it's the same gap defense in depth always had. Even a well-verified, well-authorized request can still, once permitted, reach far more of the network than it strictly needs to. Bounding that, making sure a compromised or misbehaving service can only ever reach the small slice of the estate it actually needs, rather than everything reachable on the same flat network. Is next episode, Microsegmentation, Blast Radius Containment in East-West Traffic. If you're building systems that need one consistent answer to who can access what, not 6 different ones scattered across 6 services, subscribe, and I'll see you in the next one.